Okay, well, here we have a very cool application of linear algebra, which is going to help us for differential equations. We learned back in differential equations that every nth order linear homogeneous differential equation has n linearly independent solutions. Moreover, if y1 through yn is a set of linearly independent solutions, then every solution is of the form y equals k1c1, k1y1 plus k2y2, dot 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 plus k2 knyn. This is something that we saw many times in differential equations. The point is that if we have different functions, it's worth it for us to know if they are truly linearly independent of each other, so we can know if they are the n solutions of the differential equation, and that's when comes enter Wronskian. A Wronskian is a determinant based on these functions. Y1 through yn are n different functions, and if we have a Wronskian, we make the top row of our determinant all the functions. The second row is all the derivatives, then the next derivative, until we get down to the bottom, till we have an n by n matrix. So, for example, if my functions are 1 minus x, 1 plus x, and 2 minus x, and I stick them into the Wronskian, 1 minus x, 1 plus x, 2 minus x, the first derivative is negative 1, positive 1, negative 1. The next derivative is 0, 0, 0. If I take the determinant, I get 0. So the Wronskian of these functions is 0. Whereas if I have the functions x, x squared, and x cubed, put them in my Wronskian, I put the functions on top, and I keep on going down derivatives. So the derivative of x is 1, the derivative of 1 is 0. Derivative of x squared is 2x, the derivative of 2x is 2. X cubed derivative is 3x squared, derivative is 6x. And if I take the determinant here, I get 2x cubed. So 2x cubed is the Wronskian of these, these three functions right here. And now we get down to one of the coolest functions in the world, or the coolest test, I should say, the Wronskian test for linear independence. If y1 through yn is a set of n solutions of an nth order linear homogeneous differential equation, the set is linearly independent if and only if the Wronskian is not identically equal to 0. So, for example, in this case, it's equal to 0 no matter what the x value is. This one here, this second one here, could be 0 if x equals 0, but it's not identically. There are also values of x where it's not 0, like if x equals 1, it's not 0. So identically equal to 0 means it's always 0 no matter what the x value is, such as the top Wronskian. There's bottom one, which means these top functions here are not independent, but these bottom ones are independent. I want to note a remark on the side, very important. The test does not apply to an arbitrary set of functions. Each of these functions must be a solution of the same linear homogeneous differential equation of order n. So you can't just randomly take, here we just randomly took things to show you an example, but for the theorem to work, you can't just take random things. It's an amazing theorem, and it ties together linear algebra and differential equations in a beautiful way. And I'm going to make another video right now to just give a couple examples of how to use the Wronskian test.